I call this magical process a bit matrix transpose. And it should be an instruction. Not because it deconflicts scatters, sorts elements, and counts group memberships, or because it's exceedingly simple to implement, being a fixed wiring of bits from input to output, but because it fills a hole in the vector instruction set. All other methods of moving data from column to column currently in the instruction set pull information into the column from somewhere else, but there's no way for a column to specify a destination column where its data should be sent to. This fills that hole, permitting a whole lot of things that were hard before, like reversing a permutation to send data back where it came from. The operation is exceedingly simple. Every output element gets one bit from every input element, with its position in each determining where it will go to and reflecting where it has come from. In Intel's inimitable pseudocode that they describe all their instructions with, it would look like this. This unfolds into a family of 10 BMT operations, with represented every pairing of input and output element width that doesn't exceed the register width when multiplied together. Byte to byte, a 64-bit BMT in each quad word and its own inverse. Word to byte and its inverse, byte to word, both 128-bit BMTs. Word to word, its own inverse, dword to byte, and its inverse, byte to dword, all 256-bit BMTs. And finally, double word to word, and its inverse, word to double word, both 512-bit BMTs, and quad word to byte, and its inverse, byte to quad word, also 512-bit BMTs. It can also be useful to define two more. An interleaved word-to-word operation, where the lower 16 bits of each input dword are transposed into the lower 16 bits of each output dword, and the upper 16 bits likewise, since this allows a one-to-one transfer of information from one dword table to another. And I can also imagine a dword to dword operation from two input registers split into two parts, where one gathers the first 16 dword results from the lower half of all 32 input registers, and the other gathers upper halves of all 32 input elements into the remaining 16 dword results. But since it isn't an instruction yet, I currently emulate the members of this instruction family with a series of currently available operations. The family members I make most use of are the word to dword and dword to word variants. This is the dword to word process in assembly language. The core is the byte to byte BMT on the 8 quad words of the register. Then, before and after that, a byte permute and or a byte shuffle rearrange the input and output into the right places to achieve the same result as the higher order operations. Put a variable rotate in front to shift bits into column selection positions, then some permutes and masks and 2 vpop counts below, and you have everything you need for happy scattering of 16 elements into 32 piles. Swap the first and last instructions with some adjustment of the indices, and you can throw 32 elements into 16 piles instead. The first line rearranges bytes in each 16-byte lane so that the low bytes from each word are all in the first quad word, and the high bytes are in the second quad word. The second and third lines combined replace the upper half of the lower 4 bytes of each quad word with the lower half of the second 4 bytes, and the lower half of the second 4 bytes of each quad word with the upper half of the first 4 bytes. The fourth and fifth lines repeat this at the dword and nibble level, swapping the upper half of each nibble of the lower half of the dword with the lower half of each nibble of the upper half of the dword. The sixth and seventh lines repeat this again with words and bit pairs. This results in each byte of each lane containing the result byte numbered bit from each of the 8 input words in that lane. This would be the end result for a word-to-byte operation. But then we use a byte permute to bring the byte results from all the lanes together into D words, giving the completed result we want. For several examples of using bit matrix transposes, see my other video. But a summary of uses I have found so far would be for scatter deconflict, where it generates a table of index increments for the index source tables, as well as for the selected column scatter index table, in just 13 microops. Can be used for the pre-radix sort element counting for multiple sort stages in a single pass, and for multi-group membership counting as well.